Okay, we'll go through this really quickly, but stop me if you have any questions. So, station one, water and hexane. Who can remind me what we saw there? Okay, thank you. Okay, we have this vial, and they had two distinct layers. They were both clear liquids. One was on top of each other. Why do you think that they were separated? There were three words that I told you were important for understanding this little activity. Like, dissolves, like. Turn to your neighbor and remind them what that means, please. Okay, so like dissolves like is a way of saying similar polarities tend to attract each other. So polar things tend to attract polar things. We know that polarity is when there's an uneven distribution of charge in the molecule. We know that nonpolar substances have the charges evenly distributed, and therefore they don't have one end that's more negative or more positive than the other. So things that are nonpolar tend to stick with things that are nonpolar. Things that are polar tend to stick with things that are polar, but nonpolar and polar don't usually mix. And so what can we conclude about those two layers? One was polar and the other was nonpolar. Now, the big challenge here was to figure out which was which. Don't just say water was the bottom layer because it's clear. That's not good evidence. So real quick, hexane, are there any partial charges in here? Barely. Okay, the bond between hydrogen and carbon is really fair. And I'm going to run into trouble drawing these. But so the partial charges are tiny on the positives. And I would make corrections on your sheet if you didn't quite do something right, because you are definitely responsible for knowing this stuff. All right, so the partial charges are tiny. I'm not going to draw them all, and of course this just messed up as well. But do they average out? Where's the average of the partial charges? Smack dab in the middle for both the positives and the negatives. Is hexane polar or nonpolar? Nonpolar. So all of the partial charges cancel out. There is no overall molecular dipole. There's a lot of ways you can say that. All right, let's take a look at graphite. So when you slide your pencil across the page, you are depositing these millions and millions of carbon atoms. And in graphite, they're in these sheets, these endless two-dimensional sheets. So the two-dimensional sheets are held together pretty strong. I'm sorry, the atoms in a single sheet are held together pretty strong. I mean, look at each carbon. It has like 3 bonds around it. But the connections between one sheet and the next layer are pretty weak. So when you slide your pencil, those layers slide apart and they deposit on your page, and that's how we read it. Make sense? There's also some clay in there. So who's more electronegative, carbon or carbon? They're the same, right? So can anything in here be polar? We have to have a polar bond to make anything polar, and we don't even have a polar bond. So this is nonpolar because there are only nonpolar bonds because of the same electronegativity. Do water and hexane mix? Clearly no. It must be because one is polar, the other is nonpolar. Yeah, and I hope you remember from biology that water is polar. Or just from that whole unit we just did. When we do Vesper on this, we're going to find what's our name of our geometry? Bent, and what's the bond angle? Yeah, about 109.5. Are all bents 109.5? No, good. All right, here's the question. Do graphite and hexane attract each other? Well, okay. How about do graphite and water attract each other? No, they definitely don't. So this is our clue to figure out which layer is which. So this isn't intuitive, counterintuitive, but this heavy side was always facing up, which is not what we would expect. If we had a coin and stuck some wad of bubble gum on the bottom, we would expect the bubble gum side would land down more often because it's the heavier side. So who can tell me what's up? What about graphite? Yes? Right. So graphite and hexane are both nonpolar, and this is really important because that means they would rather be with each other than for either of them to be with what? Water. So like dissolves like. Birds of a feather stick together. Nonpolar sticks with nonpolar. So I think you've just figured out for sure which layer was which. Are there any questions about this section? Can we tell whether this car has been waxed? It looks like it has been waxed, okay? Wax is nonpolar, okay? Fats, waxes, oils, all of those are nonpolar. And so why is the water like beating up? Like literally it is making the smallest portion of its water droplet in contact with this nonpolar wax. So sure, wax is hydrophobic. Why do we say that? Wax is nonpolar. Water is trying to minimize its surface area that is touching this thing. Have you seen this anywhere else? I think you saw this with another experiment we did, and we'll talk about that. Let's jump to that right now. Sulfur. So sulfur forms these rings. It can be flat, or it can be in 3D. Is sulfur polar or nonpolar? Everybody. It has to be nonpolar. It's only made of the same element, and so since none of the bonds can be polar, because all the electronegativities are equal, this can't be polar at all. So what evidence do we have for that? Do we have any other evidence for that? It floated on the water. I want you to write that down and then question yourself there. Did it float? Let's see if we can say something a little bit more specific about what we observed there. Because I would disagree with using the word float here. Okay, water has surface tension, and that's because water has this strong intermolecular force called hydrogen bonding. But what I'm asking is, would you agree that sulfur did not want to mix with the water? Okay, so sulfur did not want to mix with the water. If you noticed, even if you sprinkled the sulfur all around the top of that beaker, it still came together and clumped. Why did it do that? To minimize how much sulfur was actually touching the water. So even if you spread it out all over, you probably noticed it clumping together and forming this little sulfur berg, right? Because it only wanted the smallest amount of sulfur to actually be in contact with the water. And I'm saying the words want here. It didn't want anything, but like dissolves like. And so when nonpolar is in contact with polar, that is not a favorable interaction. So why did it appear to float? Boy, I'm giving you some hints about the word float. Is sulfur more or less dense than water? Let's go back. It is denser. Check your work on this. Sulfur is more dense than water. How do you know? As soon as we added the mystery liquid, it sunk. That is true. So we know that denser things tend to sink. Okay, so that is another reason why this word float is not so good, and we want to be careful not to use that. So what happened when you added the mystery liquid? Pretty neat, right? So first of all, a lot of times you'll see as soon as you hit that drop, the sulfur shoots to the other side. Did anyone see that? Which is really interesting. Um, And sometimes if you're lucky, you'll even see that drop, like kind of attack. It appears to attack this clump of sulfur, kind of like a paramecium. I didn't see that so much on Friday, but and then you get like this sulfur rain, like acid rain, and then eventually it all has ended up on the bottom. So did we change the polarity of the sulfur? No. Did we change the polarity of the water? No. Did we change the density of the sulfur? No. Did we change the density of the water? But clearly something happened. Turn to your neighbor. Think about it. Okay, so we didn't change any densities, and we didn't change any polarities. So how in the world did we get these things to mix? And we have to look down here at this guy, which is actually a picture of the mystery liquid. Is this polar or nonpolar? They're the same. This is just a picture of it using atoms. Oops. And then the other one is a picture of it showing the bonds. Oh my goodness. Is it polar or nonpolar? Neither? Nope. Both. It's both. Okay. Does anybody see the part of this strange looking molecule which would be nonpolar? All of the gray and the blue. Sure, this is a nonpolar chain. How do we know that that's nonpolar? Carbon, hydrogen, right. The average of the charges would be basically right here. The average of the negative charges would be right there. Okay, and then let's look at this guy. This is just one of them. Oh my. Hold on a second. Okay, so we just said that this long part is a nonpolar, we sometimes call it a tail, and then this part is a polar head. This is the shape of a detergent molecule, and there's a difference between soap and detergent. Um, there is a difference between soap and detergent. It's a little bit beyond the scope of what we need to talk about right now, but soap works in a similar way, okay? How many of you have ever tried to wash a greasy pan with only water? It doesn't work. Why not? Grease and water have different polarities, right? So the grease has no incentive to dissolve in the water, and so you can wash it away. But then as soon as you add just a drop of dishwashing liquid, what happens? It allows them to mix, and here's why. Okay, so here's here's the same molecule drawn like this. Okay, so we've got the polar part and the nonpolar part. So water, polar, nonpolar. Polar. So around here are all the water molecules. So do the water molecules want to be around the head or the tail? They want to be around the water molecules want to be near the head. What do you think would go inside? Something that's nonpolar. In this case, it was sulfur. So we've got the polar water, which is outside, and the nonpolar substance. It could be oil, it could be grime, it could be sulfur, right? Shampoos work in the same way. If you ever see like sodium lauryl sulfate, that's basically what that molecule is. Um, so does this look familiar to anybody? Kind of like something from biology. It looks like a cell, like a phospholipid bilayer, except what's different? It's only one layer, because we know in biology the phospholipid bilayer, since water is the primary component of the cell inside and out, we remember from bio that we've got these guys, but then, I'm not going to draw all of it, but then we have another layer on the inside, because we have mostly water on the inside and water on the outside. And why do we have that hydrophobic tail? And why do the hydrophobic tails get close to each other? They're both nonpolar, okay? And do you remember that that allows nonpolar molecules to effuse through the cell membrane? That's why we have a hydrophobic tail as well. So I think that I've talked enough about this one. Are there any questions? Yes. That's a good question. So we had so much less detergent than soap, sulfur. We had a lot more sulfur than detergent, correct? But even though we did that, there's a couple reasons, but basically we don't need, since this is a big old molecule, there don't need to be as many of them to surround this thing. We call this a micelle. It's like a little bubble, like a little detergent bubble. And it actually facilitated the mixing because the sulfur still doesn't want to touch the water and the water still doesn't want to touch the sulfur. But it's kind of like a matchmaker that gets them closer together. And so we can wash the sulfur away. We can wash the grease away by using this molecule. I'll let you think of, was the mystery liquid polar or nonpolar? Finally, last one. This one's the simplest yet also the hardest. I kind of enjoy it. So what happened? So when we did 5 plus 5 equals 9, 9.4. 5 plus 5 equals 9? Okay. So when we mix the water, which was exactly 5 mils, and the methanol, which is exactly 5 mils, we lost mass. True? I'll let you think about that. We actually did not test for that. What we tested for is volume. Is there a law of conservation of volume? Not that I know about. So water, Lewis structure, HOH. Methanol is going to be CH3. How'd you do on these? Okay. Vesper geometry for water, of course. Bent, which is going to make it polar because we have a partial negative and partial positives. And how about methanol? This one's a little bit trickier to draw, especially when I don't actually have space for it. So there's our CH3, and then now we've got an oxygen, 1, 2, and then we've got a hydrogen. So CH3 over here, is this part superpolar? No, carbon, hydrogen, pretty similar. But what about this one over here, OH? Oxygen is very electronegative, which means it's going to pull some positives from there. Is this a polar molecule? We've got a negative side, and we've got a positive side. Why is that important? First of all, did you see them mix? Did the water and methanol mix? Sure thing. Does that make sense? They're both polar. Okay. Do you think that they attract each other or repel each other? They attract each other. What happened to the density when we combine them? The density increased. What do we have to do to increase the density? It seems like we have to pack more stuff into the same amount of space. How do we get that done? Anybody know? Well, okay, you could say we were dissolving the methanol into the water. Somebody said they saw really, really tiny bubbles. Really, really tiny bubbles. Okay. What was happening? Long story short, these were attracting each other, and when they attract each other, they pulled each other closer. The water molecules got to squeeze in between the methanol molecules. And the result is they took up less space than they did before. So I can draw an example. So OH. So basically the methanol molecules made a little bit of a, there's a hydrogen bond right there. I didn't draw it very well, but the methanol molecules made these kind of cages, and then the water molecules, because they were also polar, were able to squeeze in there and make, ooh, that would not be a connection. Anyway, didn't draw it very well, but do you kind of understand? Methanol's larger. Water molecules, because they attract, could attract the methanol and come in and fit in between the methanol molecules even better. And so the volume decreased. We didn't lose any mass, okay? That's against the law. Are there any questions?